if you take the large omega, okay, so all this is in, so this is analyzed from here onwards. So I'm not going to do it explicitly, but this comes from a paper by Candelas, Philip Candelas, 1980. This is PRD 21, page 2185, 1980. So the problem that you have is the R functions, the radial functions, you can solve them numerically, but it's hard to get a feeling for how they behave. Now, we do know how they behave in certain limits. We know how they behave near the horizon. We know how they behave for large R. We know how they behave for small omega. So he shows that indeed the unrenormalized expectation value in any of these states, in Bowler, Hagelhagen, or Unruh, is coming from, it has this type of divergence. You can certainly see this near the horizon. You can just apply this asymptotic near the horizon. Now, it really isn't trivial to do all this for many reasons. We've got in here, this mu contains an infinite sum over L. So any asymptotics that you do have to be uniform in L. Okay, so that's not trivial to do. If you're interested, you can go to the paper and see exactly how he does it. Also remember, the divergent term is state independent. I stated this at some stage. The divergent term is always, does not depend on the quantum state. This divergence, this ultraviolet divergence, this large omega divergence, is exactly the same for in all the quantum states.
For those three, or
in any, it's called the Hadamard state. Hadamard state means that it has this type of divergence. So there are states which are not Hadamard. And in fact, they're not, so what do we mean that they're not Hadamard? But even after you subtract the divergent term, this renormalized thing, this renormalized expectation value, still diverges. So the divergence of this unrenormalized term is not completely given by this, it's called a Hadamard form. This is called a Hadamard form. So if the divergence is of this type, you say that the state is a Hadamard state. Now, in fact, Unruh and Bowler, so I'm going to give the expressions now, I'm going to tell you the properties, the physical properties now, but they're not regular everywhere in the space-time. So in fact, they're not Hadamard everywhere in the space-time. The Hartle-Hawking, in fact, is. I'll give you another properties. Okay, so this is what you have, and then you can start, you can go to Candela's paper, and you can start doing asymptotics, large R, near the horizon, and so on. Another trick that he uses is the fact that because a divergent term is state independent. So, okay, first question. Does this diverge or not?
Yeah.
Yes. We need to renormalize it. Does this diverge or not?
It shouldn't, if you take the divergence.
Right. In principle it shouldn't. Does this diverge or not?
Don't diverge.
It doesn't diverge. Why not?
Because you have taken the divergence of both.
Yeah. Because this is state independent, this is actually phi squared renormalized minus phi squared Bowler renormalized. This is because it's state independent. It's exactly the same in the Bowler state and the Unruh state. You can do this for any two states, psi and psi primes. And this is regular. In principle, it's regular if they're Hadamard states, or in regions where they are irregular. Okay, so that's a trick that he uses as well, because renormalization. So renormalization is a very hard thing to do in general, because we don't know R in and R out explicitly. So that's another trick that he uses. Okay, so let's look at the properties. Polar state. So I'll just give, as I said, I'm just giving the properties. You can go for the details. You can go to the paper. So it goes. So the polar state diverges. It goes to infinity as the point in which you evaluated goes to the horizon. So indeed, the polar state is not regular on the horizon. It is not Hadamard on the horizon. By doing this renormalization, still gives you divergence. And this is just a physical property of the state, if you wish. I'll give you. Let me explain this a little better. So near infinity, it goes like this. Now this is little. It's called little o. Little o means that it decays faster than 1 over r squared. Okay, it's not capital O. Capital O could include 1 over r squared. This tells you it does not, it decays faster than 1 over r squared. That's what little o means. If it decayed like 1 over r squared, there would be radiation. Radiation decays like 1 over r squared. This tells you that there is no radiation at infinity. By the way, this is evaluated in a free-falling frame, i.e. frame regular at the horizon. Okay. So, for example, in crustal, capital U and capital V coordinates, they're regular on the horizon, and so these are, I'm referring to the component, in which coordinates are you evaluating this? That this infinity is meaningless if you are using a frame which is irregular on the horizon, like the Schwarzschild frame is irregular on the horizon, t is equal to infinity as you approach at r equals r plus, I mean at h plus minus. So the Schwarzschild frame is irregular on the horizon, and so it would be meaningless to say that this is infinity because it could be a property of the frame. In order to infer physical properties of the quantum state, you want to evaluate this R set, this transcendency tensor, in coordinates which are regular on the horizon, so that if this really is diverges, it is a property of not the frame that you've chosen, but of the state. So polar, we say that polar, so no radiation. So polar represents a cold star. Okay? Cold because there's no radiation coming out. Star, not a black hole, because you want the surface of the star to be outside the event horizon, because you've got divergence on the horizon. And like I said, it's the equivalent of, or you've got Schwarzschild, I'll do this for a second. Unruh, like I've already advanced, it represents a black hole evaporating. That's why it's so important. It really is an astrophysical black hole. So you evaluate the transcendency tensor in the Unruh state, renormalized, and it has this behavior. So in matrix form, is TR theta phi coordinates. Okay, TR theta phi also in this direction. This is as R goes to infinity. So this is just, this bit here is just a luminosity. L. So this tells you the key is like 1 over R squared, and it's the Hawking radiation.
Is it on this BL omega?
Sorry?
BL omega.
Yes. Yeah.
So
It's a transmission coefficient.
ah,
Now, this is as R goes to infinity. You want to go to, so R equals infinity could be in chi plus or chi minus. You have to go to U and V coordinates in order to tell whether you are in chi minus, chi plus or chi minus. So this, by the way, this diverges both at H plus and H minus, not just in one of them. In here, if you go to, in U and V coordinates, you can see how it's empty. There's no radiation in the U and V coordinates. You can see it's empty at chi minus. There's no radiation to chi minus, but there is flux of Hawking radiation. That's chi plus. At the horizon, it is regular at H plus. Again, when I say, every time I say anything about regularity at H plus or minus, I mean in a frame, in a frame regular at H plus. And it diverges, it's infinite at H minus, and again I mean in a frame that is regular at H minus. So UNRU represents an evaporating black hole. Okay, H minus, it is irregular at H minus, but H minus does not exist. Okay, that would mean that there's a white, there's a white horizon. So remember, an evaporating black hole is what we did whenever we drive Hawking radiation. We had an H plus, we had no H minus. H minus does not form in gravitational collapse. So UNRU models the black holes that we have at the center of our galaxy are modeled by the UNRU script. And Harvard Hawking.
What?
Yeah.
Shouldn't? When you say that the euro represents the vertical of the iris in there,
I mean, what I really mean, by the way, is a quantum vacuum around that black hole.
because shouldn't be the Hawking the previous one that is from the collapse of the star?
Right?
Shouldn't the would represent the vacuum of a black hole in the center of the galaxy shouldn't be something like the collapse of a star.
Yeah.
Not of a eternal black hole.
No, it's not an eternal black hole, it's an evaporating black hole.
Oh, but everything, all this thing was taken account on
Yes, in an eternal black hole, because that's what I said on Monday, which is the capital up modes and capital up bar modes are defined on the eternal Schwarzschild spacetime, but they're chosen in a way that model this behavior. you can define modes in whatever way you want in eternal Schwarzschild spacetime, and they're chosen in a way that they model this. And it was due what I said the other day. It's the relationship between their positive frequency, capital up modes and capital up R modes, are positive frequency with respect to a affine parameter on H plus and H minus. H minus. H plus. I forgot. One of the two of them. H minus. Okay, just I thought it was H minus, but then it replies it's oh yeah, okay, yeah. So H minus. So the relationship between the affine parameter on H capital U or capital V, the relationship between the affine parameter on H plus and H minus and the affine parameter on sky plus, which is U, is just the same. The log exponential behavior between those two affine parameters is just the same as the one we had here between a null geodesic crossing the horizon, the affine parameter along a null geodesic crossing the horizon. The relationship between that affine parameter and the affine parameter on sky plus, which is little u, is just the same as there is between capital U. So this is an evaporating black hole. That relationship is just the same as between capital U and little u in an eternal black hole. And that relationship, that logarithmic relationship, is what causes everything. It's what gives you, the relativity properties and the Bogoliubov, the beat and the Bogoliubov transformation, and the relationship between the vacuum in one sky plus and sky minus. The really important thing is how you define modes which are positive frequency with respect to some time. Put time in quotes because little u, little v, capital U, capital V are not times, they're null coordinates. But anyway, as a loose terminology, we call them times. So the modes are positive frequency with respect to some time. That really determines everything, that determines your vacuum state. Which time do you choose? And the relationship between different times, the type of relationship between different times, for example, whether it's a linear relationship or it's an exponential relationship, that will tell you, that will determine whether the vacuum states defined with respect to those two different times, what is the relation, whether one contains particles of the other one, or they are actually the same vacuum state. If the relationship between the two times is linear, the two vacuum states are the same. The same way that it was linear between here and here, the relationship between the affine parameter along H sky minus and the affine parameter along the null geodesic that's crossing the horizon, that relationship between the two affine parameters is linear, and that doesn't change, it doesn't create particles. The relationship between the affine parameter along a null geodesic that crosses the horizon, future horizon, and that null geodesic really represents, in some sense it represents H minus. This is kind of the equivalent of H minus, if you wish. So the relationship between the affine parameter along that null geodesic in the evaporating black hole spacetime and the affine parameter along sky plus, which is little u, that relationship is exponential or logarithmic, depending on how you go. That relationship is just the same as in Schwarzschild spacetime, eternal Schwarzschild spacetime, capital U along here and little u along here. The relationship between the affine parameter that we call lambda along this null geodesic and the affine parameter on sky plus, which is capital little u, this relationship is just the same as between capital U and little u here. That's why, the Unruh modes, these upgoing capital up or capital up R modes, serve to model an evaporating black hole, to model Hawking radiation but defined, although they are defined in the eternal Schwarzschild spacetime.
the vacuums, Bohr vacuum, Unruh vacuum, and Hartle-Halting vacuum, only differs from a choice of observer.
Okay, that's one way of putting it here. It differs by you're expanding the field using modes which are positive frequency with respect to some time, and it is true that that time can be, you can think of that time as being the proper time along a proper time of an observer. And in fact, and I haven't done this, but you can look at particle detectors. You can particle detectors or observers if you wish, and you say, okay, do they get excited or do they not? Well, if you define a state which is using positive modes which are positive frequency with respect to a certain time, the observer that has that time as its proper time will not get excited when the field is in that quantum state. So this Bohr state is the equivalent of Riemann vacuum in flat space-time. Why is it? Well, number one, because Riemann vacuum, you can do the calculation in Riemann vacuum, it also diverges on the horizons. And like I said the other day, the Riemann vacuum is defined by the state which is annihilated by some Fourier coefficients. And these are what are these? Which Fourier coefficients? Well, the ones that you have whenever you expand the field in terms of modes which are positive frequency with respect to the proper time of a Riemann observer. So you can do the calculation, and then you'll see that a Riemann observer, a particle detector which follows the whirlwind of a Riemann observer, which is uniformly accelerated, we won't be excited whenever the field is in the Riemann vacuum. Hartle-Hawking is the equivalent of the Minkowski vacuum state. In what sense? Well, first of all, in the sense it is regular everywhere, like I'm going to say now. Minkowski is regular everywhere. And also, Minkowski is defined by using modes which are positive frequency with respect to inertial observers in flat space-time. This means that an inertial particle detector in flat space-time won't get excited when the field is in the Minkowski vacuum state. And a Riemann observer will, because the Minkowski vacuum has not been defined using modes which are positive frequency with respect to a Riemann observer, but with respect to an inertial observer. I haven't let you ask the question yet, sorry.
My point is that it looks like Bohr, Unruh, and Hartle-Hawking states are describing the reality according to different observers on the eternal Schwarzschild background.
No. So these statements are. So I haven't done particle detectors, and that's why when you said observer. So this is observer independent-ish. Well, that's not quite true. Sorry, that's not quite true. Well, what is true? You can create an invariant, a scalar invariant from this. You can do t-squared-ish. You can create an invariant from this, and you'll find that that invariant diverges on the horizon.
But still the average value is state dependent and the state is observer dependent.
Well, why is it observer dependent?
For instance, to define the Bohr vacuum, you use the proper time to define the positive frequency modes that define the Bohr vacuum. You use the positive time with respect to free-falling observers in eternal Schwarzschild black hole. And then by doing a choice of coordinates or a change of coordinates, so changing from another observer's point of view, you define the set of modes that describes the Unruh vacuum And then by another change of coordinates, you define the Hartle-Hawking vacuum. So the only difference between these three is the observer that is looking at the.
But we could have done everything we've done without mentioning the word observer. So I'm giving you an extra layer of physics, if you wish, but nowhere in the maths there has been. You can give it an extra interpretation in terms of the way you're doing it and that I said, but you know.
The notion of positive frequency, it sounds like it is too arbitrary. So if you don't choose
It is a choice, yeah.
So in that sense, by making this choice in that eternal Schwarzschild background, you get the street quantum states. Then I can see how I understand the argument that the calculations are background independent. So doing the calculation on a collapsing
Observer dependent. Background dependent?
in the sense that by doing the same calculations in a collapsing star background, you will yield the same results at the end. So how can you say that? How can you pick the interpretations for the Bohr, Unruh, and Hartle-Hawking states, given that it doesn't depend on the background? How can you say that this is the interpretation of these quantum states?
What do you mean it doesn't depend on the background? You mean whether I choose this one or this one?
Yes.
What's the question? How can I?
If you are, suppose that you know that beforehand that the background is the eternal Schwarzschild spacetime.
Yeah.
Now define these three vacuums in the eternal Schwarzschild background.
Eternal Schwarzschild does not exist. It does not exist in reality, by the way. But, yeah.
In the particular setup, when we are on an eternal Schwarzschild spacetime, why do we have different interpretations for the physics described by Bohr, Unruh, and Hartle-Hawking states when they are describing the same quantum field on the same background spacetime?
Because you can have different states in the same. The field is in a state, and you can have the field can be in different states.
And each state is different from the other because we are choosing a different observer.
That's one way of putting it.
So
We're choosing they're positive because they're defined as being positive with respect to different times.
So how can you give this interpretation of cold star or a black hole in thermal equilibrium with its own radiation when there is so much freedom in choice of these things? There is way too much freedom in the choice of state to assign physical meaning for that.
I'm not sure. There's too much freedom
In the choice of
Yeah.
in the choice of the notion of positive frequency,
Yeah.
in order to be able to assign physical interpretations for what comes out of a choice. So it sounds like the Aula physics is dependent of your choice of positive frequency. This is a choice in the end of the time.
Yeah. In some way, I can choose the field to be in a state or a different state.
Yes, but they are.
You can be in the Minkowski state, and then I can excite it as well. I can say, okay, it has one Minkowski particle, it has two Minkowski particles, it has 10 Minkowski particles. So the field can be in the Minkowski vacuum state, or it can be in the one particle Minkowski state, or two particle, or the Wiener state, and what does that mean? So depending on which state the field is in, different observers will measure different things. If it's in the one particle Minkowski vacuum, an inertial observer in flat space-time will measure one particle. That will say the field has contains one particle.
Okay.
Okay, so the Hartle-Hawking state.
Could we define only the capital in and capital in bar states and use the little word and try to describe the space-time with only a white hole?
I think so, yes. And in fact, I'm not going to have time to talk about Kerr, but in Kerr, there's a difference. It's not a static space, and it makes a difference whether you do it with respect to one or respect to the other one. I'm not sure. I don't think in Churchill that makes a difference. I have the feeling that in Churchill, if you do what you said. Oh, sorry. Yes. I think it will be the time reversal of what we've done. Yeah. If you use the up modes, little up modes, you get zero division sky plus and probably a flux through maybe sky minus zero. I think so. I think you'll get the time reversal of the understate.
Makes sense.
Okay, Hartle-Hawking state. So this is as r goes to infinity. So what this tells you is there's no TR component. The TR component is 0. That tells you there's no flux. There's only a TT component and a RR component. That tells you there's a bath. Okay, there's no flux of energy, and it's just radiation taking a bath just outside the black hole. So this is bath of black body quanta, and it's regular at H plus and at H minus in a frame regular and at H plus minus. So H represents a black hole in thermal equilibrium with its own radiation.
The affinity is both of square products and
Yeah, I think so. Because it's totally symmetric.
The RT term would represent the flux of particles.
Yeah.
And this
The proper way to look at this is by going to UV coordinates. And you see.
What does this mean? The term of 5 term?
So there are pressures, angular pressures, I suppose. Shear.
You could expect this in a slightly symmetric space.
Well, what do I mean? So if there was a phi, the shear would be if it's a phi r coordinate, a phi t coordinate, an angular and a non-angular coordinate. But if it's t theta, I think it's just a path. You can go to x, y, z coordinates instead of.
Wouldn't be like
It's
a,
just energy.
an angular direction.
Um, maybe.
It seems.
I always just look at TR component because that's really what gives me the flux or not flux or path or not path. That's that. That's the course. Let me just say a couple of words about. Oh, we've got this guy. Care. I'll just say literally 2 words. In care, understate is essentially the same. It does not have many more external properties. Bowler, as a state which is empty, scribe plus and scribe minus, does not exist. There is no state which is empty, scribe plus and scribe minus. The reason is there's something called Unruh-Stravinsky radiation, which is kind of the quantum equivalent of so-called superradiance. So basically, in the modes, whenever we quantize the modes, we take omega from 0 to infinity. In care, that's for the in modes, but for the up modes, you do it for omega tilde from 0 to infinity. Omega tilde is omega minus m, angular velocity of the black hole, angular rotation, angular velocity of the black hole. So that contains, you can rewrite this as an integral from 0 to infinity d omega, and an integral from 0 to m omega. And this is the so-called superradian regime, omega tilde negative, that's superradian. So that tells you that you just can't have something empty. You just can't, you're always going to have radiation at infinity. You know, there's no state, you can't define a state in Kerr space-time which is empty at infinity. That's in the root, so that's for the Bowler state, it does not exist, or if you wish, the Bowler state contains this superradian radiation, this Unruh-Stravinsky radiation. Unruh is essentially the same similar properties. That's important because astrophysical black holes, you know, the metric is Kerr, and Unruh is meant to represent astrophysical black holes. If you wish, you have the extra bit. There's a contribution in the Hawking radiation. There is a contribution from these superradian modes as well as the non-superradian modes. Hartle-Hawking state. So Hartle-Hawking does not exist. So there's no, the astrophysical black holes are radiating Hawking radiation. They're not in thermal equilibrium with their own radiation. It would represent, if you could put the black hole in a mirror, if you wish. If you put, mathematically, you put boundary conditions, reflective boundary conditions for the field at some radius away from the black hole. The state of the field would really be the Hartle-Hawking state. So for example, people are interested in this. The reason why it's relevant is because if you go to the laws of black hole mechanics, which are, people believe they mirror the laws of thermodynamics. You want a black hole in thermal equilibrium because you're talking about thermodynamics. So Hartle-Hawking represents a black hole in thermal equilibrium with its own radiation. So it's important for the laws of black hole mechanics, or people who do ADS-CFT correspondence. ADS is essentially a mirror. Okay, you've got negative cosmological constant, and you've got a black hole in thermal equilibrium with its own radiation whenever either you put a mirror by hand, just impose reflective boundary conditions, or you have an ADS space-time. So the Hartle-Hawking state is relevant for that. Something that nobody seems to know, and I don't understand why that's the case, but people, Frolov and Thorne is a Nobel Prize. I'm not sure you should be recording this. So the equivalent, the Hartle Hawking state, Frolov 1989 thing, tried to define state, the equivalent Hartle Hawking state. They constructed it, they said, okay, with respect to these modes, blah blah, and happy days, this is good. It represents a curved black hole in thermal equilibrium. I think they say that you have to be near and off the horizon. But that's been shown later, in fact, by my PhD supervisor, Aula and Stanley, that that's not, well, it just doesn't exist anywhere, not even close to the black hole. So Aula and Stanley, 2000, showed that Frolov is the Frolov state is irregular everywhere. People still use it, people still talk about it. I think in the original paper by Hartle and Hawking, they also go to Kerr. They do mostly their things in Schwarzschild, but they also talk, okay, just, you know, there's an equivalent, there's a trivial equivalent in Kerr, and then Frolov defined it, and it's just not well defined. So people talk about it, people do Kerr CFT correspondence, where the field is in the Hartle Hawking state for Kerr, and it's just not well defined. Now the Kerr CFT correspondence is a bit funny. If you do it in the extremal Kerr case, the temperature is zero, so it's a very delicate way of defining things. But people should be careful about talking about a Hartle Hawking state in Kerr. Any questions on this?
A lot of this.
Well, I'm in my office all the time, so you're welcome to come and ask me. Okay, so the next thing is going to be the exam. So I haven't corrected the previous exam. I'm going to, which is bad form for me, I'm going to try to do it as soon as possible. I'm going to email you the result so that you know it before, as soon as possible, hopefully by tomorrow. And the next thing is the exam next Wednesday.
Just a silly question.
Yeah.
Is the exam from the quantity theory approach to sum to here or everything?
Sorry?
The first.
Oh, I see. The exam is just you're asking the exam.
Yes.
From what the material which was not included, all the material up until today, which was not included in the first exam.
So, 3 dot, so.
I can't remember the section number, but I think I started Hawking radiation. So, from Hawking radiation onwards, I think I was in the middle of the start of Hawking radiation. So I include the whole of Hawking radiation onwards. Thank you.